Great. Thank you. Okay, welcome to the M-Cube weekly seminar. Today we have Qinghong Zhang. She's a professor in the Department of Atmospheric and Oceanic Sciences at the School of Physics in Peking University. She got a PhD at Peking University back in 1999. And those of you who've been here for a while will remember Qinghong here as an ASP postdoc about 20 years ago, a little over 20 years ago. She is presently the director of the International Coordination Office of the High Impact Weather Research Program at WMO, also the Secretary General of the China Committee of the World Weather Research Program. Her current research involves changes in high impact weather in the context of global warming, hailstorms, and convective initiation. And right now she's going to talk to us about this very interesting problem of smartphone pressure observations. You know, there are zillions of these things, and so she's going to tell us about the smartphone pressure data, statistical characteristics, bias correction, and applications in analysis and forecasting. Qinghong, it's a pleasure.
Thank Rich for your introduction for me. I'm so happy to come back. I still remember it was the last time I gave seminar here is in the 2002. Now so many years passed, but I'm happy to come back again. Today I'm going to talking about something about the smartphone pressure data. And first I'd like to thank Jenny Zhang, who is my co-author in this room, and also my students Rumeng Li and Yuyao Cao and Jiming Sun. And we all know our planet is experiencing a rising of the number and the increasing intensity of extreme and climate events in the warming world. And according to the IPCC R6 report, the amount of the hot stream has been found increase in most areas of the world, and especially in the high latitude. And additionally, over 50% of the world's surface has observed a rise in heavy precipitation. And according to the WMO report, that the peoples in Africa, South Asia, and South and Central America, and the small islands are 15 times more likely to die from the climate disaster. And these disasters has displaced 3 times as many people as war. And these countries bears a disproportionate burden in terms of mortality and economic losses from these extreme weather or climate events. And the high impact of weather events is mainly due to the extreme weather has been intensively observed around the world. I give an example as the 2021, and we can show the location of the most severe cases. As previous studies show, the earlier the warning was issued and the less would be lost. So it was in last year, the UN Secretary General announced a new action, this early warning for all, to ensure every person on the earth be protected. However, only 73 countries had the early warning system until the 2020. And according to the WMO report. And this plot, which is designed by the value chain by the Brian Golden from Met Office, I summarized the process of the warning system from observation, weather forecast, hazard forecast, and impact forecast, and warning and decision. And when the warning system is in operation, the flow of information is predominate down the value chain from the left to the right. And this needs it happen in quickly and accurately and reliably to maintain the value of the information. And smartphone may act as a deliver. And then now is the return flow that is in the bottom from right to the left is still crucial because it is providing the updates from the real situation. So the warning producer can maintain their situation awareness and help to the model verification after disaster. And now we know the smartphone, we have camera, and the user can take pictures. They take the weather and the disaster or some impact picture and upload to the app, and then use the AI technology, and we can use that information to do the model validation after the disaster. So if we want to protect everyone on this planet, our model should be based on the kilometer scale, right? And that would bring huge challenge to the global observing system. And the advent of the smartphone has introduced one of the solution. And with this, because the smartphone now equipped with GPS and some sensors, and we can measure the pressure and the temperature, and even some smartphones are equipped with the light sensor, and we can measure aerosols. So this could be an eco-friendly approach to obtain the high-resolution data. Among these sensors, the pressure has more stable error than other sensors. And it can directly measure the ambient pressure and has less affected by the temperature and wind environment. And here is a video. I can show you how it works.
There are two chips in this housing, a circuit for signal processing and the sensor itself. The micromechanical sensor chip is furnished with a pressure-sensitive membrane. Electrical resistors on the membrane are connected together to form a Wheatstone bridge. Changes in pressure cause the membrane to change shape. An electrical voltage proportionate to the amount of distortion is created at the resistors. The change in voltage is the result of the ambient pressure. In analog sensors, the typical signal voltage generated is between 0 and 5 volts.
Okay. In this table, this gives a summary of the current research on smartphone. And you can see it has not been paid enough attention worldwide. And only the United States and South Korea, the Denmark, and Israel and China has conducted the relevant studies. I list some of the data sources in this column, and you can see some of them. That is pressure net. And I think the popular one maybe is the weather channel here. And I'm pretty sure most people in this room has contributed to the weather channel database, right? And some of the data are labeled, and some of them are not. I will spend briefly about the labeled data and the unlabeled data because they are important and it has a very significant effect on how we use them. And this plot, you can see the star I represent as the smartphone. And if there's a labeled data, that means we have the user ID. If all we have the user ID number. And then if we want to do the bias correction, we need to set up a single user model. And even you can use the linear model or the random forest and the XGBoost. And in this version, the each data is just like a mobile station, right? And for the unlabeled data, and that means we do not have the user ID. Only we have is pressure, latitude, and longitude. And that means we can only do the bias correction using the regional model. It's just like grid, the area mean of a grid, I show in yellow color. And the application of smartphone pressure can be used as the MCS tracing system, like a scoreline. And because you can see from this plot, and I take the plot from the McNichols and Mass, their work, you can see the red color represent the positive perturbation of the pressure, and during the deep convection. And after that, the pressure perturbation will be negative. And also we can detect the hurricane surface pressure system, because the surface pressure has very large horizontal gradient. And this I give the example as the Hurricane Michael 2018 from the McNichols and Mass in the 2021 research. And this hurricane is passing by here. There is a station here. The name is, I put here, I cannot see the screen. It's this KPM. And then we have the MEDIS system, and this is a smartphone. This is unlabeled data, and this is labeled data. And you can find the MEDIS system cannot derive the central pressure of the hurricane, and the labeled data do the best estimation, but still there's some different from the observation. And the assimilated smartphone pressure data into the forecasting model has showed some varying effects from the forecasting skill. Here, I just choose one of the MEDIS and Mass in 2017, and they find small improvement in 1 hour forecast for the surface pressure and 10-meter wind, but they produce large errors in 2-meter temperature forecast. But however, the final result is good, because the 1 hour precipitation forecast are improved here, right? And starting from the 2016, the Moji weather app in China, they start collecting the pressure data from the users, because we keep in mind that the data only be collected when the user open their app. So that means our data amount will largely dominate by the human activity. So I will introduce the characteristics of this data set, and then I will introduce how we do the bias correction, and use the bias correction data to do analysis in a hailstorm case. And also I will introduce how we deal with those issues using the labeled data. And finally, I will give brief introduction of how we use the data assimilation approach to try to improve the forecasting skill. And this is the data in the 2018, and we can see it is distributed on every continent of the world except Antarctica, and with a high density in the mega city area, in like Beijing and Shanghai here along the east coastline. And if we look at the very detail in the China and the surrounding area, we would find some other things very interesting over the ocean. You can see the blue lines here. I think they might come from the shipping route over there. And if they take the number out and compare with the pressure number from the AW system, and we would find the smartphone observation number has been 2 or more order greater than the AWS. And that means we use the smartphone pressure data, we might get more detailed structure of the high impact weather event. And this is the static character of the the variation, the daily diurnal variation here, and this is seasonal, this even in each month. And we can find very significant diurnal variation. And if I have 2 peaks in a day, the first is 8 a.m. and the second is 7 p.m. And they must be associated with the rush hour. And from these 2 peaks, you can imagine most of the Chinese people, they work more than 10 hours in a day. So indicating the Chinese may be one of the most diligent nation in the world. And then you can see the other thing is the seasonal variation, right? The people tend to use the weather service more in summer. I don't know why. So we do the further analysis. The first thing is we use the monthly mean temperature, pressure, precipitation, and all the variables we can, and we use the machine learning scheme to do the classification of the whole area, and then we automatically have 4 regions. It looks imagine, it's magic to separate. But this 4 region is also the nature climate region, different in China, and we can see the northern China here, and the southern in the red, and the Sichuan Basin in yellow, and the green color in Xinjiang province. Oh, I forgot to tell you, I have removed the Great South with mean hourly weather app uses less than 5. And then you can see the diurnal variation is still there. And for the seasonal variation, it's very interesting. You see the red line indicates southern China. The people tend to use the weather surface in the winter, but not in summer. But for the Xinjiang and the North China, the peak is occurred in the warm season. And for the Sichuan Basin, we have 2 peaks. One is in March and one is in August. To understand why, we do further analysis. Here we define the extreme weather is the top 0.5% of hourly precipitation and wind speed or temperature, and the bottom 0% of the temperature and the visibility. And also we defined the demand index as the usage in any day for a given grid point, and to minus the annual mean of that grid point at that hour, and divided by the standard deviation. And we can find, and this is the extreme precipitation, and the color, the red means the people cares a lot about the weather over that time, and think the people need the extreme precipitation forecast as the first level. And then is the high wind, and then is the hot extreme in North China, and cold extreme in southern China. And that may be explained why the southern China, they have the peak weather demand in winter, right? But for the north and the Xinjiang, these 2 parts, the people tend to use more weather service in summer because the extreme precipitation occurred in summer. And I want to give you one of the example is the Henan flooding event occurred in the July 20th of 2021. And I have studied this case and cooperated with Jenny and Stan. And if you know, most of you know the events. The most important thing is in that day, and Zhengzhou station, the daily precipitation was observed like 624 millimeter. And in the afternoon, from the 4 to 5 p.m., the hourly precipitation was observed as the 201.9 millimeter. It's really a huge precipitation, hourly precipitation. And we can see the the usage of the Moji weather. In the red line here, you can see the morning peak is still there, so the people still go to work that day because the warning is not very intensively. And then the highest peak occurred at the 4 to 5 p.m. So that means the people, when the extreme precipitation occurred, the people all request for the weather service. And here is another example I show you in the hailstorm day in the Beijing urban city. And the bar is the smartphone pressure number in each grade. There's 1 minute before the radar volume scan. And the gray isosurface is the 35 dBz radar reflectivity. And that you can see the number of users jump when the hailstorm passed by, and then it was drop sharply after that. And these two cases tell us when the extreme weather occur, and then we may have the huge number of the observation, right? And that may help us to understand more about the detailed structure of the extreme weather. And then we move on the unlabeled data. So I will choose the hailstorm case to show you our result. And first we do the bias correction, and we use the data from smartphone pressure data and the AWS station observation. And the most important thing, we added the land use data set, and then we do the process cross check first, and then followed by temporal and spatial average into 10 meter in horizontal and in every 5 minutes. And then we do the quality control, and then we do the bias correction using the machine learning approach. And we use the random forest scheme. And as I mentioned just now, if we deal with the unlabeled data, we have to run a regional model. So we divided our model, our study area, into 16 subdomain. I show here. The color shading is the land use. You can see the cities here. And then we choose half part of the data from June to August in that year as the train set, and the other half as the test site. And we use the station interpolation data as the real value, and those variables are the training features. And I want to highlight the land use. And we have tried first without the land use variable, and the result is not good. But after that, we put land use in. Oh, the result is good. And then we delete the train data whose pressure bias is larger than the 15 millibar, and we run the 16 independent models. And now this is the result. You can see the 16, this is the original bias, the arrow for the 16 area. And you can see the number 6 has the highest original arrow because this area, as I mentioned, is here. It's like the urban city. Maybe the people live in the high building, so that makes the pressure arrow large. And then after the correction, you see all of them are below to 1 millibar. It's very good. And here I have 2 lines. The red line means the stable, and means it's the data set appearing in both the training and the test site. And for the blue color, it means the data set only appear in the test site. And now we use that, after the bias correction, we use that data to study the detailed structure of the storm. And you can see very interesting, there is a very clear description of the cold pool. You can see the shading is the radar reflectivity, and the triangle is AWS pressure, and dot is smartphone, and the green line is the temperature from AWS. the blue dashed line here, we use it to describe the cold pool. And we can see when the convection get mature states, there's a positive pressure perturbation associated with the downstream here. And after that, the pressure perturbation got to be negative. And I think that the downdraft here will be more clear see here. We use the V-dress analysis to show what's the difference with the different input AWS and the AWS and plus smartphone. And you can see compare with the AWS input and the smartphone plus AWS give more detailed structure of the mesoscale high. Here is the shading color. And the line here is the radar reflectivity. Here. And we can make a cross-section here and to see more obviously of where the downdraft occurs, as the line here represent the vertical motion. And also we can find the perturbation of the surface pressure perturbation just under the downdraft show a positive perturbation here, showing in the red dash line here. But if we use the input as the AWS alone, it only gives a straight blue line here. And then we move to the next part is how we deal with the labeled data. And we choose 3 hurricane, not hurricane. In China, we call typhoon, the TC Lichima in the 2019 first. And this is the TC track.
Could you remind me what's the difference between labeled and unlabeled?
Labeled means we have the user ID or the user ID number. And then we can do the bias correction, follow that user.
Oh, okay.
Unlabeled means we do not have the label ID.
Okay, so you expect higher quality with labeled?
Yeah. So normally it's for the labeled data, we don't need that will be very high resolution. But for unlabeled data, if we can good result, we need is very high density. And here, I just compare with the unlabeled and the labeled data. You can see for the unlabeled scheme, we'll find some systematics error here, but for the labeled data, it looks good. And then we do the further quality control, and that means in every grid point, we calculate the difference between the upper quartile and the lower quartile as the IQR, and consider the smartphone observation as 1 IQR higher than the upper quartile or the lower than the lower quartile as outliers. And then we can see we have even better result. And with this approach, we can reduce our MAE from 0.8 to the 0.5, and the bias has reduced from 0.299 to the 0.150. That's a good. And then we compare the minimum sea level pressure from the best track and given by the Shanghai Typhoon Institute, and from the station and from the labeled smartphone pressure. And here from the 3 cases, we would see, the first we would see the smartphone that is showing in the purple color estimate lower minimum sea level pressure than the stations. And then that is not a surprise, right? Because the smartphone has more dense resolution than the station. And the other things we can see the best track always underestimate the minimum sea level pressure around the 0.7 to 2.7 millibar. And then I call the president of the Shanghai Institute, Typhoon Institute, to tell them this. I asked them how you define the minimum sea level pressure in your best track, and they told me they use the wind, the maximum wind, to do something. They have a file. They just keep the. I always think it's just a statistical rule to make that. So I think I just give you one example here. When the typhoon center is here, and the triangle is the station, and the dot is the smartphone, you can, for this case, and we have a lot of observation near the center. So I would say that here, and the smartphone can be the good application of the minimum sea level pressure. And then we move to the last part, is the forecasting. And for this part, I choose labeled data. And I choose the one of the case occurred in Beijing in the June 30 as 2021. And there is a hailstorm formed here over the mountain at 5 p.m. and is going down the mountain and entered the main city of Beijing. And we have a lot of data in the city with the smartphone pressure. And before we do that, and I notice the previous study, no matter they use 4D var or 3D var or INCAF, and they use the default surface pressure arrow, and we see 1 millibar. And we all know the observation arrow is an important factor. It depends how we trust the background analysis or we trust the observation, right? And that invariable is the plus of instrument arrow and the representativeness arrow. If we have a high resolution observation data, the representative arrow will be small, right? And I give you some example for our case. For the two different time, you can see our user is in different location, right? It's a little bit different. And the arrow, we can estimate using our AI technology, and we found the arrow is less than 1 millibar. Most of them are between the 0.2 to 0.6 in this range. And then we try to do our experiment design. We designed 4 experiments. And the first 3, we just follow the previous study, which is control with no data simulation. And the second is we use the AWS station data in. And the third is we use the smartphone data in, but we keep the pressure arrow as 1 millibar as a constant. And then the last experiment is we let the arrow change with the time and change with the location. And the bottom is our data simulation cycle. And I'm going to show our result of the last one, the third cycle. And that result is from the 12th to the 14th UTC. And we can see the pressure arrow, the 2 meters a second, and the wind, U wind and V wind. And we can see during most of the time of the surface pressure. After the 24 minutes, the pressure arrow estimated by the phone observed simulation got the lowest arrow bias, right? And see the same with the 2 meter temperature. And the green line here is showing is the same, the lowest arrow with the V wind, but the U wind is not good, but you need the V is more important because the V is defined how many moisture we have, right? And then finally, we can have the 2-hour accumulation precipitation forecast in 1 millimeter intensity, showing the blue line here is improved a lot from the control, and also is improved from the AWS station simulation. And we see the 5 millimeter intensity is the same. So when we use the last simulation, when we use the changeable observation error, we can get better result. And now is the summary. And we think compare with the traditional operational station observation, the smartphone pressure data, they can show 2 or more order of magnitude in urban area with dense population, and especially during the extreme weather events. And it can give us more detailed information on the mesoscale structure in a hailstorm, and more accurate estimate of the minimum sea level pressure, and when for the landfall TC cases. And we can use the AI technology to enhance the quality of the smartphone pressure data. And those data has the potential to improve the weather forecasting ability, at least in the short term. And I think for the future research, there might be 2 directions. The one is we can increase our model resolution to higher, for example, like to the 100 meter, because in Beijing city, our data is like 100 meter resolution. And another approach, maybe we can do the data simulation in the global model. And modern science, I think there's another important thing we need to think about, is we do not have a global standard of the smartphone data policy. And the different people, they think in a different way. But like for in Africa, if I take an iPhone and travel to a country and measure the pressure, and that will be illegal for that country. So we have a lot of stuff to do in the future, I think. And I think the smartphone can increase our weather forecasting value by changing the value chain into the value network, I think. Because we can deliver our weather warning information through the smartphone, and also we can collect the data, do our observation with the smartphone, right? And this is my last slide. And what's this? I think this is the users in China. In every minute, they require for the weather service. And I think this is the most beautiful part for the science, is to serve people, right? And I think maybe in the future, maybe every citizen can own their own smartphone, and they can also use that phone to as an observation station for themselves and for others. And this is our publication here, and that's all. Thank you so much.
The paper is open for questions, comments. Jimmy.
Yeah, 2 questions. So one was you showed the app. It's only when the app is open it was reporting the pressure. Is that true of the Weather Channel and other things? Do US smartphones always report the pressure, or just when the app is open?
I don't know the situation of the Weather Channel.
Okay.
But the Cliff Mass, they have a lot of paper. Maybe they describe about them. But I know for the Moji weather app, actually they can measure temperature too. But the temperature designed is for the battery temperature. So it's a little bit harder because you need to write two equations to solve the air temperature.
So the other question was related to the data simulation. The last experiment you showed was that 40 bar.
3D bar.
3D bar even, and the only extra data was the pressure. You're not simulating like rainfall or anything else. It's just the standard.
Yeah, just the pressure to do the comparison. Yeah. We just take the pressure from the AWS station observation. Yeah.
So I had a question as well on the assimilation of these. Are you thinning these observations in ways or super robbing them, or how are you handling this mass amount of smartphone observations? Can you elaborate on that a little bit more?
And can you ask the question? The first part I didn't.
Oh, I'm just curious how you're actually assimilating these observations in terms of, are you assimilating all of them that pass the quality control, or is there some super robbing that's going on, or a lot of data thinning? Can you elaborate on that a little bit?
We only use the data after the bias correction. Can you answer the question too? But you are my co-author.
I can follow up with you later.
Oh, no. No, we didn't do that. I didn't, sorry.
No, okay. Questions from this side here? Yeah, so the possibility of AI, is there anybody working on just skipping the model and just putting in the AI and predicting?
Yeah, I think the AI, the model is free on web.
Yeah.
Unless my students deal with them.
It
It's
may be
free to
possible
it's free to download.
Yeah, it may be free to train.
Yeah, they are
train
free.
it just on the
train.
data.
Yeah,
Yeah.
yeah.
All right, let's see if we have no further questions or comments. Please join us for cookies and coffee and further conversation. Thanks again, Qinghong.
Thank you.